Okay. Now making a buffer, so the recipe for buffer. So we'll use the buffer equation. I quote and unquote the word, the equation, because it is not a buffer equation yet. However, you can call it a buffer equation for convenience because of this idea that I like better than using a real buffer equation. So you're going to have the conjugate pair, right? The acid and the base at equilibrium to each other. So you write like this as usual, as if you have weak acid alone. So if you have just one chemical, weak acid, then you write it out like this. If you have two chemicals, then this is not equal to that. But the Ka expression is the same. One chemical, this is equal to that, right? Because they both come from one chemical. So when this is X, this is also X. Now, when you prepare for buffer solution, you're going to externally add the two chemicals. So they are not equal, although you can make them to be equal. Okay. So this is a sodium salt, a real chemical, sodium A chemical, and this is the corresponding weak acid. Okay, so these are two chemicals that you calculate for the experimental concentration and mix the two. Then this is the concentration you want it to buffering for, to maintain at this particular pH. Okay, so anybody can memorize this formula, right? So this is my buffer equation. Okay, so again, this ratio will indicate the two chemicals externally added is not ionized from one chemical. Okay, keep that in mind. Ratio added. So the H plus will correspond to your pH desired, whatever the level you want to maintain at. So rearranging that, right, the Ka is a table value. You want to pick one acid that is nearest to your desired pH. Okay, the pK. The pK is closest to your buffering pH. Okay, so you set it up like this, table value over that, then a ratio. Okay, so for example, the ratio, this is just an example. The ratio is ratio. If you end up with 0.1, then it means is 1 over 10 millimole, 1 millimole over 10 millimole, or is same thing as 10 millimole over 100 millimoles, or 100 millimoles over 1,000 millimoles. They are the same as ratio, etc. So once you calculate the ratio, you have a decision to make. Okay, this is ratio, right? How much of the chemicals ratio you need to put in to achieve that goal. Then these are decisions to make. So along that line, keep in mind that this represents different number of moles, absolute number of moles. Then of course, when you have more number of moles, then you have a greater buffering capacity. Okay? Otherwise, the ratio is just indicate ratio. Any question at that point? Okay, here comes the real buffer equation that you are familiar with. And it is actually derived from the Ka expression. So if you keep on going, minus log, incorporate the minus logs for P function, then do things like this, and this is how you end up with the Henderson Hasselbalch equation. Okay, so this is your salt, chemical externally added, salt, and this is the corresponding acid externally added into the same solvent. Okay, salt over acid, and it's a plus. Okay, I have difficulty to memorize this formula. I always get confused with plus or minus, you know, and then which one is on top of another, whether it's acid on top or the base, you know. Depends on the sign here. If this is minus, then you flip it upside down. So for me, I would simply write out the Ka expression and then start from there, you know, it's the same thing. But here is the convenience because the pH is set up for you. Then you just plug in the pK value and then the salt and the acid. Okay? So this is your formula. So there's a buffering pH. Then you want to match closest Ka to that and then determine the ratio. So you plug in a number here, and then plug in the table value in here, right? So that you will get the ratio. Okay, so here is one way to prepare a buffer because often that you have one chemical but not the other. For example, you want to make up this buffer. You know that you need acetic acid and its salt. Well, acetic acid may be readily available in your lab, but sodium acetate is a little fancy. You know, it's a salt that you may not have available. Okay, so you have only that available in the lab. And sodium hydroxide also should be readily available in the lab. So once you have that and that available, you can generate the mixture. And end up with the same thing as mixing with that. So the idea is right here. Right? Here is your acid, and here is your base. So this is acetic acid. Okay? And this is sodium hydroxide. You add into that and calculate so to see how much of the acetate is generated. Right? So this is reacted, and this is generated so that this is not totally reacted. Let's say half of this is reacted. Okay, when half of this is reacted, then half of it must have been generated as that. So now your final solution will have half of this, half of that is your buffer. Okay, so keep that in mind. You could make a fun exam question because it's practical.